Alright, so to really understand Bohr's hydrogen emission spectra experiment, we need to first look at some properties of light, right? So light is also known as electromagnetic radiation. So we're going to call it EMR for short, right? And light, the reason it's called electromagnetic radiation, first of all, radiation is basically transfer of energy through some kind of medium. Transfer of energy through a medium. Okay. It's electromagnetic because it will affect electrical and magnetic fields, right? So we don't need to know that in too much detail, but I do want to kind of explain what this notion of a medium is. Okay, so a medium is any background or environment that a particle or energy, right? That particles, let's say out particle, particles or energy can move through. Okay, so we're going to look at some types of mediums. But some common types of mediums include air, water, right? Certain other types of fluids, and remember, a fluid is basically a liquid or a gas. Okay, so mediums include, for the most part, fluids, but it's not restricted to fluids. You can also use solids as well, right? We don't really commonly use solid mediums because it's really, it's hard to travel through a solid, but it can pass through solids. So solid mediums do exist, right? It could be like wood or metal or whatever, right? But another medium that we need to also look at is a vacuum. So a vacuum is an empty medium. Okay, so an example of vacuum is space. Space is a vacuum, right? Because it's a completely empty medium. There's no particles present, right? So these are examples of mediums, and energy and particles can move through these mediums. Now, light is composed of discrete units called photons. Okay, so what is a photon? Because a light is made of these discrete units, a discrete unit, once again, is a quantum, right? So a photon is a quantum of light. It's the building blocks, it's the single building blocks of light, okay? Now, what really is a photon? Now, I would think about a photon as a little packet of energy, right? It's kind of like, this is like a packet, right? Let's say that this is the energy that a photon contains, right? This is one photon. So this is one photon, okay? I'm just kind of illustrating this for you, but really light is composed of multiple photons, right? Like these little packets of energy. Like, I like to think about them as like the sugar packets you get at like a coffee shop, right? And each sugar packet, which contains sugar, the sugar is the energy molecules. Like, it's just energy. Like, I don't know if energy is a particle, but these sugar packets contain energy, and each packet is one photon. Okay, so this is what a combination of photons could possibly look like, right? And light is composed of trillions and trillions of these photons, right? There's a huge debate whether these photons, are just energy-like, or maybe they kind of have mass, right? We're not going to spend too much time looking at that. But we need to understand that light is composed of multiple photons. Okay? And we want to kind of study the energy of the photon. Now, for us to understand the energy of a photon, we need to first think about what is light, right? So light is a wave, right? Specifically, it's a type of wave called a transverse wave. Okay, so let's first explain what a wave is. What is a wave? Okay, so a wave is a disturbance in a medium. Okay, so a wave is a disturbance in the medium, right? And what a disturbance is basically a medium is made up of particles, right? Unless it's a vacuum, and in that sense, vacuum will not be disturbed, right? Mediums, with the exception of vacuums, a vacuum is an empty medium, with the exception of the vacuum, are composed of particles. What happens is when things move through that medium, it's going to shift that medium. It's going to shift the particles, right? So basically, particles or energy moves through a medium, it may affect the particles or the medium. Right, it may shift the medium. Okay, now the medium's particles, unless it's a vacuum, the medium particles can shift in two main different ways. Okay? So the way we're going to look at this is, in one case, right, let's say that these are some of the photons that are basically passing through a medium. And let's say that the medium here, let's say the medium is air. Okay, so the medium, we're looking at air. Okay, we're seeing light move through air. Okay, so light is moving through air. Well, these photons are basically, let's use orange for the photons. These photons are moving through air, right? And what's going to happen here is these air particles are basically being pushed outwards. Okay? In some cases, they might be pushed out larger than others. Okay, so you can see that the air particles, they're being pushed out almost 90 degrees to the direction of travel of the photons. Okay, so if the medium is disturbed 90 degrees to the direction of travel of the energy or particle, this is what we call a transverse wave. Transverse wave. So transverse wave occurs when the medium is shifted perpendicular to the motion of the particle or energy. Okay, so whatever direction the energy is traveling in, the medium is going to travel in a 90-degree direction. Okay, so light is a transverse wave. So what we'll usually express light as in terms of graph, okay, on the y-axis we'll have displacement, we'll have delta y displacement. So displacement on the y-axis, right? And we're specifically looking at the medium, right? And this, on the x-axis, we could have time of travel or travel of the photon, right? Or we can even look at the x displacement of the photon, doesn't matter, right? We could have delta x displacement of photon. Or we can look at this as time, it doesn't matter, it's the same thing, right? And the graph here should kind of look like that, right? And basically what's going to happen here is in certain cases, the medium is going to have a highest displacement, the maximum point, right? So this maximum point we're going to refer to, so this is a maximum point, and we can even have lows or depths of displacement called minimum point, okay? So let's look at some of the wave properties of light, the transverse wave. The other type of wave is called a longitudinal wave, which is iconic of sound, right? Longitudinal waves. We're not going to really focus on longitudinal waves, but a longitudinal wave, this is like, sound is basically a pressure. It's a pressure gradient, and basically sound is due to collisions of air particles, right? So where there is no air, there wouldn't be any kind of sound that's being created. So let's say this pressure wave is moving this way, right? And let's say that the medium is air, okay? So we're going to still use the medium as air. Okay, so if the medium is air, the air particles actually move in the same direction as the pressure wave. It kind of pushes it pushes the air particles, right? So it's like you can imagine that air particles are being pushed in one direction. So the medium moves in the same direction as the wave, the energy or particle itself, right? So a longitudinal wave, and this is just for clarity's sake, but a longitudinal wave, we're not going to really look at this. A longitudinal wave is where the medium is shifted in the same direction as the direction of the particle or energy moving through it. Okay, so that is what a longitudinal wave is. Now we're not too concerned about longitudinal waves. So let's go back to our definition of light being a transverse wave. So we're going to look at light, and I'm going to look at light being a transverse wave. I'm going to use this diagram. Let's say that this is time, and then this is the displacement on the y-axis of the medium. Okay, so this is the displacement of the medium. We could use some kind of units for this. It could be meters, right? And this is essentially what the light waveform will look like. Okay, and we'll keep repeating, right? And this repeating notion, this is what we call a periodic function. A waveform is a periodic function. A periodic function has a repeat, right? And this is on the x-axis we have time, and a periodic function has a repeat called a cycle. So a cycle is called a repeat, right? And each cycle occurs at a certain amount of time, right? And this is what we call the period. The period is the time it takes a wave to complete a cycle. Okay, so this is really important, right? So we can understand that a cycle will exist from, let's say this is time 0. We can see that it repeats all the way to here. Okay, so this distance here is the period, because the length, so basically this is one cycle, right? Because then we just repeat all over again, and the time it takes on the x-axis, we have time. The time it takes is a period. So we can understand that period is measured in seconds. Okay, so the period is measured in seconds, right? And so we can understand that the period, I'm going to use t to represent period. So we're going to use t. Oops. So we're going to use t to represent the period, right? It's just something that we use conventionally. Now we can understand that the shorter the period, the faster the wave. Okay, so the shorter the time it takes, or the less time it takes to complete a cycle, the faster the wave is moving. So let's investigate that using two graphs, right? So we can understand that this is, okay, so I'm going to do two transverse waves. We're just going to look at this by inspection. Okay, so once again, waves are periodic functions. So periodic functions, they'll repeat, and each repeat is called a period. If I look at these two, right, and if I look at when it repeats, so you can see that in the first wave, and we'll call this wave 1, we'll call this wave 2. In the first wave, the wave will repeat using this time interval. So we'll call this delta t1. So this is the time interval that it takes, right? And we can call this the period, right? So this is t1. This is period 1. When we look at the repeat or the cycle for wave 2, it basically encompasses this much. So this is delta t2, or we can call this period of wave 2. Okay? You notice here that period of wave 1 is greater than period of wave 2. And we can also understand that if we look at wave 1 and wave 2, wave 1 is moving slower than wave 2. And the reason wave 2 is moving faster is because of the fact that wave 2 actually completes more cycles per given time amount, or allotted time, than wave 1, right? Let's say that the total amount of time here is constant. So from 0 to the end point, right? Let's call this TF, right? So from TF, from 0 to TF, it's the same amount of time, so it's a constant amount of time. So you can see that wave 2 completes more cycles in that allotted time period than wave 1. Okay, so if the period of a wave is greater than another wave, then wave 1 is moving slower than wave 2. Okay, so the period can also be useful for helping us to determine which wave is moving faster, right? A faster moving wave is more energetic, right? So it'll tend to have more kinetic energy. Kinetic energy is the energy of movement. We'll look at this in a bit. But we want a way to quantify how fast a wave is moving. So we use this term, it's called the frequency. I think it's a different color for this, but the frequency is the number of cycles a wave will complete in a second. Okay, so the frequency, and for the most part, I'm going to use F for frequency. In textbooks, you might see it using a V sign, but I think F would just be more intuitive. And the frequency here is the number of cycles that a wave completes in a second, and this is actually inversely related to the period. So the frequency is 1 over the period, right? And if we look at this in terms of proportionality, the frequency is inversely proportional to the period. So what does it mean by saying it's inversely proportional? Well, if the period increases of a wave, the frequency will decrease in a wave. Okay? And as the period decreases in a wave, the frequency will tend to increase, right? So, and this makes sense if we kind of look at this waveform. We can understand that the frequency of wave 1 and the frequency of wave 2 can be compared, and the frequency of wave 2 should be greater than the frequency of wave 1. Okay? Although the period of wave 1 is greater than wave 2, right? So higher frequency is associated with more cycles being completed in a second, and there's more cycles being completed in a second, the wave is moving faster. So as a result, higher the frequency, the higher the speed of the wave, right? So the next kind of relationship that we can kind of look at, we're going to be looking at the speed of the wave. We're going to say V is the speed of the wave through a medium. Right? And we can understand that V should be directly proportional to the frequency, right? So the more number of cycles that a wave completes per second means that the wave is going at a higher speed, right? If the frequency goes up, the wave speed goes up. So we can call this wave speed. And because we're looking at speed, we can write the unit for meters per second. And I did mention back here that the unit for frequency, because frequency is a cycle per second, 1 cycle per second is called a hertz. Okay, so we use this symbol, hertz. That's basically equivalent to 1 cycle per second. So frequency, the SI unit is hertz, right? So it's a cycle per second. So going back, we know that as the frequency increases, the wave speed of the wave will increase, and as the frequency decreases, the wave speed of the wave decreases. Okay. We also understand that frequency is inversely proportional to the period. So because the frequency is inversely proportional to the period, we know that as the period increases, the frequency will decrease, and as the period decreases, the frequency will increase. Now what we want to do here is we want to relate all 3 variables together. We can understand that as the period increases, the frequency will decrease, and as a result, the wave speed decreases. And as the period decreases, the frequency increases. And as a result, the wave speed increases. Okay? So we can see that the wave speed is directly proportional to frequency. Frequency is inversely proportional to period. And as a result, the period is inversely proportional to the wave speed. Okay, so this is also another proportionality that we'll understand. Together we can take all of this material and create an equation, and this is what we call the wave equation. V is equal to F lambda. Oh shoot. One one sec. I messed up. Now another thing that we need to kind of discuss here is something called wavelength, right? Okay, and this actually influences, it'll affect our period. And if it affects our period, it'll also affect our frequency and our wave speed, right? So what is the wavelength? Well, the wavelength is the distance of a cycle. The distance of a cycle is the wavelength, right? So we can understand that the larger the length of the cycle, the longer it would take to complete that cycle. So we should have a longer period, right? So if we go back and we draw out our transverse wave, right? And this is our transverse wave. We know that this is our length of our cycle. So this is our cycle. That's our length of our cycle. On the y-axis, we had the displacement of the wave in meters. On the x-axis, we have the time in seconds, right? We know that this is the length of, this is a cycle. And we know that this portion here is basically the time it takes to complete the cycle. So this is the time it takes to complete the cycle. So this is the period of the wave, right? And that's going to be in seconds, right? It could be some kind of seconds. The frequency is the number of cycles that occur per second. But the length of the cycle is given by another letter, and we're going to call this the wavelength. Okay? So the length of the cycle, just the distance of the cycle, is the wavelength, and the wavelength is going to be measured in meters. Okay? We can understand that the longer the length of a cycle, the longer it'll take for the wave to clear that cycle. Right? Like we compare two different waves. We compare this wave versus this wave, right? We can understand that if we're just looking at the physical length of the cycles, right? So we can see a cycle that occurs here, right? This is the length of the cycle. We'll call this wave 1. So this is wavelength, or lambda. We use the Greek letter lambda for wavelength. A lambda 1, and the length of this cycle here is basically lambda 2. Okay, so this is lambda 2, this is for wave 2. And you can notice here that wave 1 is greater than wave 2, right? So this tells us that the period of wave 1 should be greater than the period of wave 2, right? Because the time it takes, the longer the length of the cycle is, the longer it'll take to clear that cycle, so the period should be a lot higher, right? And we can also understand that if we look at wave 1 versus wave 2, I'm just going to write that here, we can understand that the frequency of wave 1 should be less than the frequency of wave 2. Wave 2 should be faster, it should complete more cycles per second than wave 1. And as a result, the wave speed of wave 1 is less than the wave speed of wave 2. Okay? So, because we now understand this other variable, wavelength, its relationship with period, as the wavelength decreases, the period decreases, and as the wavelength increases, right, the period increases. If we loop all these together, we can understand that as the wavelength increases, the period increases, and as a result the frequency decreases, and as a result the wave speed decreases. And as the wavelength decreases, the period decreases, and as a result the frequency increases and the wave speed increases. Okay. Now, using all of this, we can create an equation to summarize this, and this is what we call the wave equation. It's a really important equation in chemistry and physics, and it's really useful in determining the speed of the wave, which also will tell us later on about the energy of the wave. So this is the equation. V is equal to F lambda. So V is the wave speed in meters per second. Right? F is the frequency in cycles per second, also known as 1 hertz, right? Hertz. And the wavelength, which is the distance that it takes to complete a cycle in meters. Okay. Usually these distances when we're looking at light are going to be really small, specifically in the nano realm. So 1 nanometer is 1.0 times 10 to the power negative 9 meters. Okay, So it's really useful to understand this prefix nano, right? It basically means 10 to the power negative 9. Okay, but this one's probably going to be the most useful, right? Then there's also micro, which is 10 to the power negative 6, right? Beyond nano, there is an angstrom, which is 10 to the power negative 10. Okay, we use this symbol. It's A with a circle on it. Angstroms are going to be really important later on. I shouldn't write meters, but angstroms are going to be really useful later on when we're looking at bond lengths, because they're usually in the realm of this length. This one's useful. 10 to the power negative 12 we're not going to really look at. It's called a pico. The prefix is pico, right? But for the most part, we're going to understand that nanometers are what's going to be important, right? Picometer would be 10 to the power negative 12. Angstroms we don't really use for measuring distances, and then micrometer is negative 6. Okay, so this is really the most relevant equation that we can kind of show you guys. This is the wave equation. We're going to use this to now calculate the energy of a photon. Alright, so we're continuing on with our discussion of light. We need to also look at light, the speed of light, in general, right? So light will have different speeds in different mediums, but when we're looking at the speed of light, we usually consider light as a constant, and the speed of light is given by constant c, and this represents 3.0 times 10 to the power 8 meters per second. Now this is the speed of light in a vacuum. Okay, so this is the speed of light in a vacuum. That means empty space, right? For the most part, we can assume that the speed of light is an empty space, right? Usually the speed of light in air is approximated to 2.99 times 10 to the power 8 meters per second. And notice that I'm just using 3 significant digits, right? So this is in air. For the most part, we're going to be looking at this. Okay, so we're going to be doing the approximation that light is always traveling through a vacuum. Okay, so when we are looking at the wave equation for light, V is equal to F lambda, now this wave equation you can actually apply to any wave, but we're only going to be using this for light. We're going to be thinking about this as C is equal to F lambda. Okay, so the speed of light it tends to be constant. So the only thing that's going to really change is the wavelength and the frequency, right? So we can use this equation to isolate for frequency, which is c over lambda, and wavelength, which is c over frequency. Okay, so I basically got that by using algebra to the equation. Okay, so let's take a look at an example of a question. Okay, so let's take a look at this question. Determine the frequency of light with a wavelength of 562 nanometers. So in this case, we're given that the wavelength is 562 nanometers, and you got to change nanometers into meters. The SI unit for wavelength is in meters. We know that 1 nanometer is 10 to the power negative 9 meters. So 562 nanometers is 562 times 10 to the power negative 9 meters, which is basically 5.62. So what you can do is you can simplify the scientific notation, and so times 10 to the power negative 7 meters. Okay, so this is what the wavelength is in meters, right? So now that you have the wavelength in meters, what you want to do here is you want to find your frequency. So if you're looking at your equation, you're doing V is equal to F lambda, right? If you're solving for frequency, what I'm going to do here is in my equation, I'm going to divide both sides by lambda to get rid of it. So V over lambda is equal to the frequency, and then if you wanted to solve your frequency, you plug it in. Now V here is going to be equal to C, right? So we know that's C, and we can approximate the speed of light in a vacuum. We can approximate the speed of light as in a vacuum, meters per second. Okay, so the frequency is 3.0 times 10 to the power 8 meters per second, and this is divided by lambda, which is 5.62 times 10 to the power 7 meters. Okay, and then when we calculate this, you can notice here that is going to give you 1 over seconds, which is a hertz basically. And if we calculate this, I'm just going to divide the numbers separately and then look at the scientific notation by combining the bases, right? So 10 to the power 8 minus divided by 10 to the power negative 7. When we're dividing the same bases, we just subtract the powers, so we get 8 minus 7, which is 10 to the power 15. Now if I divide 3.0 over 5.62, this is going to give me 0.5338, right? And this is 10 to the power 15. What you want to do here is you want to write this in scientific notation. I'm going to move the decimal here, so this is 5.338. So when I move the decimal to the right, that means I'm multiplying by 10. So I need to offset that by dividing by 10, which means I'm subtracting 1 to the power. So I'm doing times 10 to the power 14. Now because in our question we had 3 significant digits, right? You want to change this value into significant digits. So you get 5.34. So you want 3 significant digits in the scientific notation times 10 to the power 14. So this is the unit for frequency is hertz. So this is the frequency of that wavelength. All right. So this is really useful to kind of understand. Okay, so we talked about some properties of light, specifically that light is a transverse wave. A transverse wave is basically a wave that will basically have a medium that gets shifted 90 degrees to the direction of the travel of the photons, right? So the direction of the photons. And in this case, we just looked at this whole notion of light collectively, right? Well, light is just another name for electromagnetic radiation, so EMR. So we talked about EMR earlier, but there's different types of EMR. Okay, and we looked at some of these properties. We looked at the wave equation, which illustrates that the wave speed is equal to the frequency times the wavelength. These different types of EMR are characteristic of different or specific types of wavelength and frequencies. Okay, now we don't need to discuss too much of what these intervals of wavelengths and frequencies are, but I'm just going to kind of list out the different types of EMR. So the different types of EMR, starting with the highest wavelength, it's called a radio wave. Okay, so starting here, this is going to be the highest wavelength, and we're just going to create like a spectrum. We're going to kind of just look at some of those aspects of the spectrum. Okay, so radio waves have the highest wavelength. So on the left side, we have the highest wavelength. Okay, radio waves are utilized mainly in telecommunication because of this high wavelength. Right, so your cell phone will emit radio waves, right, and so forth. Now, the other type of waves that we're going to be looking at are called microwaves. Okay, now as we go towards the right, we go towards the lowest wavelength here. Okay, so as we go towards from left to right, we have the lowest wavelength, right? One sec. So radio waves are usually between 10 to the power 4 meters all the way to 10 to the power negative 2. And there's different types of radio waves, right? We don't need to really know this, right? There's like AM transmissions, there's short waves, there's TV, there's the FM type of radio waves, and there's the radar, right? These are just different types. They're different types of radio waves that'll be used for different devices, right? Like AM and FM, you've heard of this in radios, and the TV uses different types of radio waves, right? So these are just all really examples of why we can use this in telecommunications, because of the fact that there's so many, like they're such a long type of waves. They're very long spanning type of waves, right? They span long distances. The other type of wave that we're going to be looking at are called microwaves, right? So radio waves will span from 10 to the power 4 meters to 10 to the power 0 meters, and it'll be used for devices such as AM and FM radio, shortwaves, TV, radar, etc. Right? Now, from 10 to the power 0 to 10 to the power negative 3 meters, and I'm going to use the scale of meters, we have something called microwaves. So microwaves are mainly used for energy sources, right? Like such as the Microwaves are usually high energy waves, right? And I just want to make a correction here that radar is actually a type of microwave, not a radio wave, right? In this case, they have a pretty high wavelength, but they are much shorter than radio waves, and we usually use their energy to warm or to heat up certain things. Like your microwave at home is going to basically be used to heat up your food, right? Then beyond a microwave, we're going to have infrared radiation. So infrared radiation is usually 10 to the power negative 3 to 10 to the power negative 6, right? Okay, infrared radiation, you can kind of, this is mainly just heat, right? So heat is basically infrared radiation. Like heat seekers are basically, they will look out for sources of heat or infrared radiation. Now between 10 to the power negative 6 and 10 to the power negative 8, this is what we're going to be mainly looking for, right? This is the visible light spectrum, Roy G. Biv. I'm going to use Roy G. Biv to explain what the visible light spectrum is. So this is really our mode of focus, right? So our focus is really the colors of visible light, right? And this is what's going to be really important when we study Bohr's emission spectra experiment, right? We need to understand, first of all, why all of these wavelengths are characterized this way, and their relative energies, right? So the reason that we look at the wavelengths of spectral light as Roy G. Biv is because as we go towards the color red, the wavelength increases. As we go towards the color violet, the wavelength decreases. Okay, so this is really important, and we're going to explain what that is, right? So this is really our focus, just to complete our discussion about these types of wavelengths, right? Beyond 10 to the power negative 8, usually to 10 to the power like negative 9, we'll have UV radiation. Okay, now these wavelengths are not too important for our discussion, so we don't need to understand this, but UV radiation is really highly energetic. It's really short wavelengths, and this is really one of the reasons why we need to wear sunscreen in really high intense sunlight, because some of the sun's rays contain UV radiation, and this UV radiation, these UV rays, they penetrate deep into the skin, right? And it's one of the reasons why they'll warn you guys about skin cancers and so forth, right? So these are highly penetrating waves, okay? So this is really highly energetic waves. So you can see that as we decrease the wavelength, the energy is decreasing. So we'll talk about this relationship later on. X-rays are really useful in studying soft and hard tissues in the body, right? So X-rays, right? So they're really highly penetrating scans, right? That's one of the reasons why when you go to the doctors, the doctor will give you a lead vest to cover certain regions where you're not exposed to the X-ray, where you don't need to have the X-ray being exposed to. It really basically blocks that energy from damaging those tissues, right? So this is short wavelength, high energy is the whole name of the game, right? And beyond X-rays, we get gamma radiation or gamma rays, right? So beyond this, as we keep going further, we get gamma radiation. Now gamma radiation, I'm going to use this gamma sign, which looks like this. Gamma radiation is really highly energetic, right? There's very little mass associated with this. It's highly energetic, right? And it's highly penetrating. And really the only thing that can block this is lead, right? So this is really the radiation that comes from nuclear waste, right? Now for the most part, we're just going to be looking at our spectral colors, right? So if you take white light and you shine white light through a prism, right? And that prism is basically, what the prism will do is it'll actually bend light and make the light travel so slow that it actually splits into its spectral colors. Okay, so we're going to look at some of the spectral colors: red, orange, yellow, green, blue, indigo, and violet. And we stated that red has the highest wavelength of spectral light, and violet has the lowest wavelength. Okay, so now let's kind of relate this notion of energy of a wave and its wavelength. So let's look at some of the let's look at the relationship between the wavelength of a particular light ray or electromagnetic radiation and its relative energy, right? So we talked about different types of electromagnetic radiations, but the type of electromagnetic radiation I'm going to be looking at is the visible light spectrum. Okay. And the reason we call it the visible light spectrum is because this is the only real wavelength of light that our eyes can actually capture, right? Some animals can actually capture infrared radiation, right? I'm not too sure if animals can capture UV radiation, but some animals like snakes can capture infrared radiation, so they can actually see heat, right? Our eyes, unfortunately, can only see the visible light spectrum. And the visible light spectrum will usually span from 380 nanometers to 760 nanometers. Okay, so this is an approximate range. So for the most part, you don't need to really know this, right? And at the 380 range, we said that visible light can be remembered using this mnemonic, Roy G. Biv. Well, at the highest end of the range, the colors will appear red, and at the lowest end of the range, the colors will appear violet, right? So as you go this way, the wavelength is the highest, and as you go this way, the wavelength is the lowest. Okay. Now let's kind of relate this in terms of our talk with energy, right? Well, when we're looking at, we know that according to the wave equation, V is equal to F lambda, right? As the wavelength increases, the wave speed decreases, and as the wavelength decreases, the wave speed will increase, right? So wavelength is inversely proportional to the wave speed. Okay, and the wave speed is also associated with the energy of the wave, specifically the kinetic energy of the wave. So let's define kinetic energy. So EK is kinetic energy, and if we're defining kinetic energy is the energy of a moving particle. Okay, so it's the energy of moving particle or energy. Okay, so let's say, right, it's the energy of movement. Let's summarize it like that: energy of movement. Okay, so EK is the energy of movement, and kinetic energy actually has an equation. It's 1/2 mv squared, right? Photons, we can say that the mass is negligible. Now, there is a huge school of debate on it, whether photons have mass or not. It does have mass. It's infinitesimally very small, right? So for the most part, let's say that EK is proportional to the velocity squared. Okay, so as the velocity or the wave speed increases, then EK, or the kinetic energy of that wave, will increase, right? So based on this notion, if we go back to a relationship between wavelength and the velocity or the wave speed, as the wavelength increases, the wave speed decreases, and as a result, the energy of the wave decreases. As the wavelength decreases, the wave speed increases, and the energy of the wave increases. Okay? So having a high wavelength is associated with lower energy, right? And having a low wavelength is associated with high energy. So as wavelength decreases, the kinetic energy of the wave increases, and as the wavelength increases, the kinetic energy of the wave decreases. Because in one case, it's where the wavelength is small, the wave is moving a lot faster. When the wavelength is large, the wave is moving a lot slower. Okay, so this is really the idea behind it. Now, the whole point of this is we want to understand the relationship between wavelength and its energy of the wave. But specifically there, we also want to calculate this, right? So when we're looking at light, right? We said that light is made up of these particles, quanta, and the quanta are called photons, right? The energy of one photon can be calculated by the equation HF. Okay, now I'm going to explain what this means, but H here is Planck's constant, Okay, Max Planck was instrumental in contributing to the quantum mechanical model, which I'll talk to you guys about later. But h is Planck's constant, and it's actually given a value. It's 6.634 times. Sorry, it's 6.626 times 10 to the power negative 34 joules per second. A joule is just a unit for energy, right? So this is Planck's constant. So a constant, that means constant is going to be the same for all scenarios. And F is frequency. So frequency is going to be in hertz, or you'll also see hertz written as s to the power negative 1. It's 1 over seconds. It's a cycle per second, right? The 1 represents 1 cycle. And energy of a photon is measured in joules. Okay, that's the unit for energy. Okay, now we can tweak this equation. So the energy of a photon is equal to hf. We also know, according to the wave equation, v is equal to f lambda, right? The frequency times the wavelength. V in this case is equal to c for light, right? So I'm going to combine these two equations together. So I'm going to take the energy of a photon and the equation for light. I'm going to combine these together. And when I combine these together, the energy of a photon is equal to, now because I have hf, I want to solve for frequency using the wave equation. The frequency here is the speed of light in a vacuum c over the wavelength, right? So instead of writing frequency in this equation, I'm going to rewrite this as hc over lambda. Okay, so this is the energy of the photon equation that we're going to be looking at. You can actually notice here that if you're comparing the energy of the photon to a wavelength, right, as the wavelength increases, look what happens to the equation, right? So this increases. When a denominator gets really small, the energy, the magnitude of that fraction decreases. So the energy of the photon decreases. So as the wavelength increases, the energy of the photon decreases. So this is one of the reasons why equations are so useful in giving us inferences, right? But it's good to understand the inferences before deriving the equation. As the wavelength decreases, right? If the wavelength decreases, that means if this number gets smaller, then the magnitude of the fraction gets bigger, so this would increase, right? So as the wavelength increases, then the energy of the photon increases. So as a result, the reason why we look at the spectral colors, Roy G. Biv, in this sort of way, the wavelength increases to the left, and the wavelength decreases to the right. To the left, as the wavelength increases, this is the lowest energy. To the right, where the wavelength decreases, we have the highest energy. Okay, so, and we can calculate the energy of the photon by just using this equation. Okay, remember that c here is the speed of light in a vacuum, which is 3.0 times 10 to the power 8 meters per second. Okay, remember wavelength is going to be in meters. Right, and Planck's constant we said earlier, 6.626 times 10 to the power negative 34 joules times seconds. Right, and the energy of a photon is going to be measured in joules. Okay, so this is the energy of one photon. If we know the number of photons that make up light, right, if you're looking at some kind of wavelength of light, right, if you have energy of some kind of wavelength of light, this is basically equal to n, which is the number of photons times the energy of one photon. Okay, so this is really the idea, right? We can call this En if you want. Okay, so n is the number of photons that makes up that form of EMR. And the EMR is going to be, the electromagnetic radiation is going to be some kind of wavelength of light, or they'll give you frequency of light. Okay, so let's take a look at a question. All right, so let's take a look at a question where we're basically using the wave equation and really Planck's equation to calculate the energy of a photon in a particular EMR array. So for an EMR array that contains 1.23 times 10 to the power 12 photons with a wavelength of 412 nanometers, determine the energy of the photon as well as the total energy of that EMR array. Okay, so let's calculate the energy of the photon. So if we're calculating the energy of the photon, we know that the wavelength of this photon is 412 nanometers. And you know what, I'm going to use a different color for this so we can kind of differentiate between the question. Okay, so we know that the wavelength of the photon is 412 nanometers. And 412 nanometers is associated with 4.12 times 10 to the power negative 7 meters, right? Because we know that 1 nanometer is 10 to the power negative 9 meters, right? So we'll basically get 412 times 10 to the power negative 9 meters. And then if I move this decimal 2 spaces, then we're going to add 2, because basically if I move this to the left, we're dividing by 100, so I'm going to multiply by 100 to offset that. So I get 4.12 times 10 to the power negative 7 meters. Okay, so we know that the wavelength is this much, and we want to first figure out the energy of a photon. So we know that the energy of a photon is, according to Planck's equation, HF, right? And we know that Planck's constant is 6.626 times 10 to the power negative 34 joules per second. We also know that the speed of light is a constant, and we're going to approximate that it is the speed of light in a vacuum. It's 3.0 times 10 to the power 8 meters per second. Okay. Now we also know the wave equation, V is equal to F lambda. In this case, I'm just going to approximate V as C. So C is equal to F lambda, and F can be written as C over lambda. So the energy of the photon equation, Planck's equation, I'm going to substitute F is equal to C over lambda and write the energy of the photon as H times C over lambda. Okay, so this is the equation of the photon. And then what I want to do now is I want to substitute this in. So the energy of the photon is equal to H, which is 6.626 times 10 to the power negative 34 joules per second. I'm going to multiply this by 3.0 times 10 to the power 8 meters per second, so for the numerator. And I divide this by the wavelength, which is basically going to be 4.12 times 10 to the power negative 7 meters. Okay, so if I crunch out the numerator, I'm going to multiply the numbers separately, and I'm going to add the powers because the bases are the same. So it's 10 to the power negative 26, right, and the seconds would cancel out, right? You get joules per meter times joules times meters times 19.878, right? I'm going to refrain from rounding off until the very end. I divide this by 4.12 times 10 to the power negative 7, right, meters. And in this case, I'm just going to divide the numbers together, and then the powers, right? If I subtract the powers, I'm just going to do it here, right? You basically will get 10 to the power negative 26 minus 7, so it's like 10 to the power negative 26 minus negative 7. I'm going to multiply this by 19.878 divided by 4.12. Okay, so that gives me 4.8247. Okay, so this is 4.8247 times 10 to the power negative 19. Okay, and this is going to be energy of photon, so it's energy in joules. And I want to use 3 significant digits, so I can round this to 4.82 times 10 to the power negative 19 joules. Okay, so this is the energy of 1 photon. So this is 4.82 times 10 to the power negative 19 joules, right? And if you want to figure out the energy of the EMR, right, so the entire wave, then I'm just going to make some space here. And sometimes use a different color to represent the next question. If you're looking at the energy of the EMR, then what you want to do is you're just doing n times the energy of the photon, and n is the number of photons present in the wavelength, in the wave itself. So 1.23 times 10 to the power 12 photons times 4.82 times 10 to the power negative 19 joules, and this is per photon. And the photons cancel out, and you can calculate the energy. So 10 to the power 12 times 10 to the power negative 14, so that's like 10 to the power negative 2 joules. You add the powers, and then you do 1.23 times 4.82, and you get 5.93. Okay, so you basically get 5.93 times 10 to the power negative 2 joules, and that's the total amount of energy that you can find in this wavelength. Okay.